Hello, everyone, again, and thank you for the opportunity. Um, Here, I will talk about what nanoplasmonic laser fusion research is, and then I will explain our considerations for the target. Then I will compare two um, open source software which we plan to use in this research, and finally I will conclude which software should we use. And I will emphasize here that this is a new laboratory, the Nanoplasmonic Laser Fusion Research Laboratory, which has started recently. It is a very large group of researchers, a theoretical group, a laser group, and there are some materials specialists and spectroscopy group. The aim of this research is to study nanoplasmonic effects of gold nanoparticles, which will be implanted inside the target. And of course, the very long-term goal is to help in some way the laser fusion research area. So thermonuclear fusion does not happen spontaneously on Earth. If we know the total energy and the usable energy, of course, and the losses, we can capture and to have very clean and affordable energy in the future for energy production, we must calculate this gain factor. And we will only achieve if we can fulfill the Lawson criterion. Currently there are two main directions that are researched: the magnetic and inertial confinement. Inertial confinement is where the density of the plasma is increased. There are two main directions of the inertial confinement fusion as well. The first one is a direct drive, which contains the target, and the laser beam hits directly the target, and the biggest experiment is in the National Emission Facility, Lawrence Livermore, where it is an indirect drive, where the laser beams come inside the hole room like this through the two holes on the top and bottom of the hole room. More than 190 laser beams excite the hole room, and X-rays then will indirectly heat up the target, which has an outside layer, an ablator, and in the first step, the target is compressed by that outside layer, and when the second step is the target is ignited and burns. That would be in theory. However, the research and the development is hindered by Rayleigh-Taylor instabilities, partly because the energy cannot be delivered symmetrically as in theory in every point of the target, and we propose the nanoplasmonic laser fusion research project to mainly avoid these instabilities from heavy ion collisions. We know that space-like surfaces can smoothly change to time-like surfaces due to the points of the shock front in these cases are not connected, not have a causal connectivity. If we hit with constant absorptivity, here is the light cone. We will see that before the light reaches the other part of the target, there is a small time-like front. However, this simultaneous ignition is only enough to heat a small portion of the target. However, if we dope with gold nanoshells, which are resonant at for example, at 800 nanometer wavelength, we can alter the absorptivity to an extent in which we might achieve simultaneous ignition faster. We consider the flat target, which has a minimized surface area. And for example, on one-sided irradiation, for example, we see that without a nanoshell, the deposited energy does not even reach the middle. However, if we alter the absorptivity of the target, the deposited energy reaches much further. Similar to two-sided configuration was already proved successful by this group. They achieved higher compression on lower with lower energy. The nanoplasmonic laser fusion research laboratory is also preparing with experiments. So the aim is to research how the gold nano implants alter the absorptivity of the target. The first target which we can use with the lasers in our institute is a dental monomer with the UDMA, which and the theoretical group, the theoretical group has to provide sufficient information for the experimental group to what setups they could use, and for that we use particle in cell method. There are a lot of peak method software which are available online that are also open source. There are also software which are not open source, however, extending those would be harder. Even open source software is hard to extend, but they at least share the code. We chose the epoch code is written in Fortran, and the Picanta is written in C++. In general, the particle and cell methods use marker particles, which are inside the cell, and they are driven with a particle pusher and finite difference time domain method, usually used for solving the Maxwell equations. The epoch code layout is also uses general leapfrog method, in which the half time step the fields are calculated. Then the particle pusher calculates the forces and the momenta using the fields calculated at half time. Then the full time fields are calculated with the resulted currents. The epoch has an input deck which is very user friendly, and in the housekeeping is usually for the calculation for the computing. There are also physics packages, and I will tell you about that later. So what I already mentioned, the necessary fields are calculated at half time. Then the particle pusher calculates the current, and the particle pusher solves the relativistic equation of motion, this one, and the current deposition scheme which the epoch uses is the Bunemann. And then also there is a particle shape, because we know the marker particles are not particles, they are representing many, for example, many electrons, and one important thing is that the momenta is usually calculated so that the shape of the particle is not taken into account. So the momenta is actually one marker particle. However, the fields that are calculated, which then will be applied to the particle, take into account the shape of the particle, for which usually this triangle shape is used, which is the fastest one, meaning that fast but not that precise, but it is more precise than a top hat shape. But in the Epoch code, the quadratic spline is also implemented. However, of course, the Epoch code does have a few features that we might need. For example, the rough box or grating or grid stretching feature. The grid stretching feature, which can be used, for example, to study Rayleigh-Taylor instabilities, and also the rough box and the grating features can study surface plasmonics. So the publications they published are very promising. The Picante code also has an advanced output strategy. The Epoch code uses this kind of strategy where our tasks write into the same file. However, the Epoch has an advanced feature that there are a group of tasks who respond to a master task, and multiple master tasks write into a file, which scales very well as the MPI tasks increase. However, the Epoch code is, the Picante code is still in beta version and has been for at least 3 years. So the modification that was made, I think, was 2 years ago in the GitHub repository. Yes. So it is not a widely used the software. However, it is very promising. It has very promising features. However, does not contain ionization, which will be very necessary in our case, because short laser pulses will be used with high energies. In the scale, in that scale, even nonlinear optics has to be taken into account. The Epoch software does include multiple ionizations, from multiphoton ionizations to tunneling ionizations, and the Epoch code is used also in the LE labs. And finally, arriving to the conclusion, the mechanical pressure-driven processes are subject to Rayleigh-Taylor instabilities. Our research group aims to solve that problem with adjustable absorption of a target. and for more realistic estimates, we need a relativistic analysis. And for the first steps of the research laboratory, we need to provide information and to use a software which is more experimental physicist friendly. So since Epoch is used more widely, I think from the two softwares, I would choose the Epoch software. But in the next in the next 3 months, I would like to implement at least a few features of the Picante, because I forgot to mention that the Epoch is very extendable, so they thought about that as well. Thank you for your attention.
So, okay, anyway, so there is a question, István, you may also see, so I could get the point, I couldn't get the point, the transparency show UDMA. What are you using? Yeah, can you see in the chat?
Yes, I see. The UDMA is our first target. It is the target which will be doped with the gold nanoshell. So our first target is not going to be hydrogen, but it will be this UDMA. So it is the whole target, which will have a length of around 20 to 100 micrometers.
Okay. Any question from here? Oh, I would have also a question. You mentioned that the first step will include some, you said on the last slide, that smaller laser with monomer targets. What do you mean on smaller lasers here? So is it ELI, or is it some much more smaller laser like in a laboratory here in the Wigner?
Oh, it is a smaller laser, like smaller than the LE laser, for example. It is much more like the lasers we have in Wigner Institute.
Oh, okay.
It is 10 to the 70 watts per square centimeter is, I think, the max intensity of that.
Oh, sounds good. So we can do this in a tabletop. We have also a question from Olena Lindley. Olena, are you online?
Yes, hello.
Please.
Yeah, I'm sorry if I missed it in your simulations description. Have you run it on GPUs? Do you plan to? I understood that it's parallelizable, but is it also easy to run on GPUs?
Oh, I'm sorry, I forgot to put it in the slide that these are MPI processes. In a longer term, we might put them on GPUs. The first step is to merge the benefit of the two software.
Thank you.
Okay, thank you very much. So any further?
I still have a question.
Lotsy, please increase your volume, please.
Okay, so my question is that in the Epoch code, we do not have compressional energy and equation of state, while in the Picante code, these are existing, and that is what you want to combine. And of course, if you reach higher nuclear densities, then even the ions, which can be protons or deuterium or tritium, are having already some interaction, nuclear interaction among each other. And then you also have electrons where, I mean, of course, the total energy density is less in there. Is the Picante code having both equation of states for the ion gas or ion particles and the electrons, or and even interactions other than electromagnetic interactions between the ions and the electrons? And which do you implement?
There are in the Picante there are a lot of unfinished, not a lot, but maybe it was me. I found a lot of unfinished functions which have to do comments on them, and the drawback of the Picante code is that it is not very well commented, so not a developer friendly. No, I did not. I could not find what you mentioned. Even so there is no ionization effect, and for the wake field, you have to have separate ion marker particles and electron marker particles.
Mm-hmm. Okay. Yeah, so there is still work to do even compared to Picante, because Picante doesn't include everything. Okay. Yeah, thank you very much.
Yeah.